Hey everyone. So today we're going to talk about this circuit right here, which is, I've labeled here just as combo 2, just because we have a combination circuit, meaning we have both series and parallel elements in it. So when you first look at this circuit here, it may not be obvious as to what elements are in parallel. You might think, oh, well, these look like they look mathematically parallel to each other, but these are actually not directly parallel to each other. This element's actually going to be parallel to this these two elements put together. And so just kind of going through this, first things first, let's label what we know from this circuit, right? So we know that our total voltage is 12 volts. So I'm going to label that here, right? We know that because we have one battery and that battery has 12 volts where our positive ends up here. So we know that when we're doing following our current around our circuit, we travel from the positive end of the battery to the negative end, since conventional current is nominally the flow of positive charges. Right? The other things we know is the resistance value of each of these resistors. So in this problem we know all our resistance values. So resistor 1 is 20 ohms, resistor 2 is 15 ohms, resistor 3, that's this guy, is 20 ohms, resistor 4 is 15 ohms, and resistor 5 is 8 ohms. All right, so we know all those values. So kind of looking at my chart here. So here today I'm not going to calculate power, so I'm not going to worry about this. So if I made this chart here, I see that in this row I'm only missing total resistance. That means I can compute that value. So looking at this here, we need to basically add up all our resistors, right? But we have to be careful with what elements are in series and what elements are in parallel. And if ever it looks like it might be confusing, just kind of chunk it off little by little. So basically find the equivalent resistance for pairs of resistors, whichever ones look easiest. So kind of here there's two resistors, or two sets of resistors might be kind of simple to add together, right? Anything that's in series is easy to add together because the total resistance is just going to add. So for example, these two resistors here, they're in the same wire, the same path here. So these are in series with each other. So what we could do is pretend we replaced these two resistors with one resistor of equivalent value, hence why we call that equivalent resistance. So if I were to redraw this circuit, so here's my battery, I'm just going to draw it as a single cell battery just for convenience. So we still have resistor 1 here of 20 ohms. Traveling along, I'm just going to draw this first loop just for my bearings, and I did not change anything in that loop. I haven't dealt anything mathematically with any of these resistors. Oops, forgot to draw that one there. And now these two resistors in this wire that has split off at this junction, now we are finding as if, or we're treating this problem as if there's one resistor of equal value. Right? So here, since these are in series, we just add them together. So we have a 30 ohm resistor over here to the right. What we could also do, I'm not going to do this in this step, but you might also see, well, looking here, these two resistors are actually in the series, the 8 ohm and the 20 ohm. So you could actually add those together and redraw it, but I'm going to leave that just as it is, just for reasons we'll see in a moment. Now looking over here, we see we have a 20 ohm and 30 ohm resistor, and we can see they're parallel with each other just based on how I've drawn it, but just kind of thinking about our current, well, our current splits into just these two possible paths, and the voltage drop is going to be the same in each of these, right? Just based on our loop law. So these two elements are in parallel with each other, so when we add them together, we have to be careful, right? So remember when we're dealing with circuit elements that are in parallel, not circuit elements, specifically resistors. When resistors are in parallel with each other, right, kind of thinking about the charges, there's more opportunity for them to travel, right? They could travel this way or this way. So the amount of resistance they're going to feel is actually going to be less. Feel is not really the right word, but the amount of resistance that they're going to come across is going to be less. So hopefully when we add these together, it'll be less. So, okay, so 1 over our equivalent resistance value is going to be 1 over our 20 ohms plus 1 over our 30 ohms. All right, so 1 over 20 plus 1 over 30 is 1 over 12. I forgot my ohm symbol, right? But our resistance, our equivalent resistance is not 1/12, right? It's 1 over the resistance, so we need to flip it, right? And you can also think of it as just cross multiplying. So we take the inverse of 1/12, that leads to our resistance value of being 12 ohms. Okay? So that's very convenient for us. Now we can redraw our circuit. So I did not touch this top resistor. Now, instead of having these two elements, we replace them with one element of equivalent resistance. And that new resistor value is 12 ohms. And this guy down here is 8 ohms. Right. So now looking at the circuit we're analyzing, well, now we just have a simple circuit with just 3 resistors in series. So we can just add up all those resistance values together because they're in series with each other, and find that basically our total resistance now is going to be 40 ohms. So in a sense, what we've done is found the equivalent resistor of those 3 together. We don't necessarily have to write that if we don't want to. Well, now this is convenient because now that I know my total resistance and I know my total voltage, I can find my total current. And what I mean by total here is the amount going through this battery. So when I say total current, that's going to be the current running through the wire that's running through our battery. So we're just basically using Ohm's law here. Remember, that's V equals I times R. So to find I, just take V divided by R. So 12 divided by 40 gives us 0.3. And current has units of amps. So we have 0.3 amps running through our battery. Now, just kind of referring back to this diagram, right? Well, if 0.3 amps is running through the battery, well, our wire doesn't split at all. So we're going to have 0.3 amps running through resistor 1. And kind of thinking about this backwards as well, right? We see here that leading up to the battery, the wire doesn't split. So that means we must also have 0.3 ohms running through, sorry, not 0.3 ohms, 0.3 amps running through resistor 5. Since the current has to be the same in this chunk of the circuit, since the wire doesn't split at all. All right, so basically, in a sense, we're using Kirchhoff's junction law, but there's no junctions, so current's the same in that wire. Okay, makes sense. Now looking quickly here, well, we see that since I know the current and the resistance for at location of resistor 1, this guy here. Uh-oh, that's not good. Let's put that back. All right, sorry about that. We can calculate the voltage drop over resistor 1, right? So we can find out how much the voltage changes. So calculating that value, we just take 20 multiplied by 0.3, and we get 6 volts. And we can do the same thing here for resistor 5, and we get 80 times 0.3, 24. Something's wrong. Oh, why did I write 80? That's 8. So I realized something's wrong because I took 80 times 0.3, I'm getting 24, which is more voltage than we had to begin with. Doesn't make any sense. All right, so 8 times 0.3. All right, 2.4. That's much more reasonable. 2.4 volts. Okay, well, looking now. So in terms of, if you're not really sure what to do, look at your circuit and try applying either Kirchhoff's loop law or Kirchhoff's junction law, right? So we kind of already mentioned the junction law where the current going into a node has to equal the current going out of the node, or node or junction as I used the word before. And the loop law, in a sense, states that the amount of voltage provided by the battery, the amount leaving has to be the same as the amount coming, or sorry, has to be dropped off at every resistor until we have a value of 0 coming back to the battery. Right? That's kind of the easy way of thinking about the loop law. So if I'm a charge and I'm traveling, right? So I'm traveling, I leave the positive end, I'm traveling through our wire, I'm going to drop off some voltage here, travel through our wire, I reach a junction, so I can travel one of two paths. Let's say I happen to travel through this resistor 3 here, so I drop off more voltage here, travel through, drop off more voltage over here in resistor 5, and then come back to the battery with 0 volts. Well, we just calculated that resistor 1, we have a voltage drop of 6 volts, and resistor 5, we have 2.4. So that means that in these two, we have dropped 8.4 volts. So if we take 12 and subtract that 8.4, we end up seeing that we have to have a voltage drop of 3.6 remaining. And we see that since we only travel through one of the resistor, being R3, that 3.6 volts has to be dropped off there. Of a similar argument, we can look through our large loop here and see that again we've traveled through both these resistors, so we have a total of 8.4 volts dropped, leaving in a voltage drop of 3.6 in the combination of these two resistors. Now we can quickly see here that we can logically state, well, if there's 3.6 dropped off between the two and they have the same resistance, that 3.6 volts must be divided evenly. So it's going to be 1.8 volts in each. So pretty simple there. Although you might ask, well, how could I have solved for that if they were different values? Maybe if this was 10 and that one was 20 ohms or something like that. Well, what we could have done, right, is applied our junction law. So we know, let's look at this junction here. Going in, we know we have 0.3 amps of current. Oh boy. Sorry that keeps happening. I'm just going to hold it since I'm almost done. All right, so we have 0.3 amps reaching this junction, so we know that leaving out through this wire and this wire, they have to add up to be 0.3 amps. Well, through resistor 3, we found the voltage drop here being 3.6 volts, so we can calculate the current running in through that wire by taking that 3.6 dividing by the 20 and getting 0.18 amps. So then logically, if 0.18 is running this way, well, the amount that's running through our other wire over there has to be 0.3 minus the 0.18, giving us a value of 0.12 amps running through this wire. So that means running through both of those resistors. Now, kind of as a check here, I'm going to take my 1.8 divided by 15, and hopefully we get that 0.12. And, oh, sorry, so 1.8 divided by 15. Not multiplied, I multiplied in my calculator. Anyway, that becomes 0.12 amps, like we had calculated, so kind of this is a check, we got it right. All right, so I hope that was helpful in kind of reviewing that circuit problem.